Hi, welcome to the e-learning video series from Anasazi Instruments. Today I'm going to talk about how number of scans affects NMR data. So first question is, of course, when or why do we change the number of scans? Well, there's a lot of different reasons, but we'll take a look at these right now. When you are synthesizing a molecule or extracting something, sometimes you get very little amount, milligrams or micrograms. In that case, we are probably going to have to increase the number of scans in order to get greater amount of signal in our experiment. Similarly, if we're looking at proton, which is 99% abundant, versus carbon, which is only 1% abundant, we're obviously going to have to do many more scans for the same amount of solute running a C13 experiment than we will have for the proton experiment. Another situation is when we have large molecules, maybe biomolecules, proteins, where the molecule itself has very low solubility in a solvent, and therefore we're going to have to increase the number of scans due to the effective amount of sample in the coil. So how does the number of scans affect data? Well, as the number of scans increases, we obviously get an increase in the observed signal. In the spectra here, we see 3 spectra with 1, 4, and 9 scans. And it's easy to see that the spectrum with 4 scans has greater intensity than the single scan spectrum, but less than the 9 scan spectrum. If we zoom in on the methylene peak in the middle there and stack plot it side by side, it's a little bit easier to compare and see what the difference is in these spectra. Here, with the number of scans 1, we get a peak height of 5.5, 4 scans, peak height of 22, and 9 scans, a peak height of 45.7. Similar to peak height, and probably more important to spectroscopists, is the integration of the area under the peaks. Within a molecule, all of the protons can be accounted for using integration, whereas peak heights for peaks that are split into triplets, quartets, doublets is much less quantitative than using the integrated peak under the entire multiplet. Notice here, though, that there is a linear relationship between number of scans for both the peak height and the integrated area. The signal is directly proportional to the number of scans. So how does the number of scans affect noise in the spectrum? So besides the desired signal that we acquire in an NMR experiment, we're always going to have unwanted noise that's present in the spectrum as well. The noise comes about from the environment, cables that are used to connect the spectrometer, thermal stress on components, and basically the overall design of the instrument. Well, previously we've seen that the signal, whether it's the integrated area or the peak height, is directly proportional to the number of scans. However, the noise in a spectrum is random and it does not co-add like real signals. In the picture below, we see that we can measure the noise in the spectrum, and what we find out is that the noise is proportional to the square root of the number of scans. So, knowing that and the fact that signal is proportional to the number of scans, we see that signal to noise ratio is also proportional to the square root of the number of scans. With that in mind, let's take a look at some data and see if we can measure these different qualities. Today we're going to be looking at how number of scans affects the data that's collected in an NMR experiment. We'll be using the NUTS data processing software. Once the demo software is installed on your computer, the NUTS icon will be on your desktop. We can launch the NUTS program and clear the license information. We're going to be using the right-click menu to process the data today, including running macros, manual integration and checking signal to noise, and using the zoom subroutine, as well as selecting slices and stack plotting arrays of data. First off, we're going to run a macro. All the data that I've collected for these experiments has the extension of signal on them, so we're going to run the AI signal macro for these. First thing the macro does is ask for a file to process, so let's go in the data folder. Notice that all the data is separated according to what type, and I'm going to process the propobenzoate H1 signal data. We'll clear the acquisition parameters window. We'll notice that we get 3 spectra. The 3 spectra are the results of 3 different experiments where on the left we did a single scan, in the middle we did 4 scans, and on the right we did 9 scans. So we're going to see how the signal changes depending on how many scans you did. Let's look at one peak at a time though. Let's hit enter to get out of the stack plot mode. We'll go into the zoom subroutine and just zoom in on a single peak within the spectrum. Click and drag through it, type Control E to expand, and hit enter to get out of the zoom subroutine. Let's go back into the stack plot mode. Recall that you can scale with page up, page down, up arrows, and also the mouse wheel you can roll. When you click in the background, a red crosshair comes up, and in the bottom right hand corner over here, the position of where the intersection of the 2 lines is shown in points, hertz, and ppm. Likewise, the height of the horizontal line is shown on the far right. We're going to use that right now. Let's click and hold the horizontal line at the tallest point on the far left spectrum, and we'll look on the right hand side for height. Comes out to 5.11. Now in the middle spectrum, we did 4 scans as opposed to 1 in the far left. So we would expect to see 4 times the signal. Let's click and hold the mouse and put it there. Comes out to 20.21, just a slightly less than 4 times, but pretty close, I would say. And finally, doing 9 times the number of scans on the right here, we would expect 9 times the signal, and that would come out to around 45 or so. We'll put the mouse up here. Comes out to 42.2. So comes out a little bit less than what we'd expected, but it scales pretty well with the number of scans. I'm going to hit enter to get out of the stack plot mode, and the thing we're going to do now is look at how the integrations compare as you change the number of scans. We saw that peak heights scale pretty well with the number of scans. Let's see how integrations scale with the number of scans. So let's go into the integration subroutine. Recall from previously that integrating a peak takes 3 clicks. The first click brings up this red vertical line. Second click defines one edge of the area you want to integrate. The third click sets the second region. We're going to set this integral value to 1. So we're going to click once in the background and have the vertical line intersect the integration line. Type the letter V for value, and when the box comes up, we're going to put in 1 for the current relative value. We're going to hit enter to get out of the integral subroutine. Notice that the integration line disappeared. We can bring that back either by typing Control I or using the menus to bring it back. So the integration for a single scan now is set to 1. When we change to the next slice in the array where we did 4 scans, we'll change to slice number 2, we see that the integration for 4 scans goes to 4, really close, much less than 1% error. We would expect then when we look at the third slice where we did 9 scans, let's do that, zoom, slice, go to slice 3, we get 9 times the integration. So what have we learned so far? Peak heights scale with the number of scans. Integrations scale as the number of scans. But integrations scale better than peak heights. And I want to tell you why right now. Over the course of an experiment, there can be slight changes in the magnetic field And so peaks get a little broader. Instead of staying tight and narrow, they get a little broader. And so for almost all data processing of T1s and T2s and other kinds of experiments like that, we don't use peak heights to process data. We always look at integrations. They're always more accurate than peak heights. Now the next thing we want to do is look at how signal to noise compares to the number of scans. So let's go back to slice number 1. I typed the SL command for slice instead of using the pull down menu. Go to slice 1. Notice our integration is 1 again, and we're going to use the signal to noise function. You can also just type the command SN. So let's do a signal to noise calculation. Notice in the left-hand side over here at the bottom, the signal to noise value comes up for this peak. It's really the signal to noise of the tallest peak on the screen. And that's coming up to 1700 plus a little change. Now, we saw that signal as far as peak heights and integrations goes as the number of scans. It turns out noise goes as the square root of the number of scans. So we would expect the signal to noise to also go as the square root of number of scans. So let's change the array to slice 2. In slice 2, we did 4 times the number of scans. So we're expecting the square root of number of 4. 2, we should expect twice the signal to noise. Let's use the signal to noise function, and we get a signal to noise of 3400 and change. So our signal to noise changed by a factor of 2 when we did 4 times the number of scans. From what we've seen so far, we can expect that doing 9 times the number of scans, that the signal to noise should scale as a square root function of that. We should get 3 times the signal to noise. So we'll go to slice 3, signal to noise. 3 times 1700 is 5100. We're getting almost exactly 3 times the signal to noise. So a couple things that we've learned here so far. Peak heights and integrals scale as the number of scans, but integrals scale better. Signal to noise scales as the square root of number of scans. So when we do 4 times the number of scans or 9 times the number of scans, we get double and triple the signal to noise. This sample that we did today is an example that's very concentrated. This propylbenzoate sample is 98% with a little bit of TMS in it. What we would like to find out is, how does this experiment come out if we're doing moderately concentrated samples or dilute samples? Is there going to be a change? What if we change the pulse width from 90 degrees to 45 degrees? There's several data sets in the data folder for you to work on and learn a little bit more about how signal and signal to noise scale with the number of scans based on concentration. Thank you for your time.